Section 5.1, Solving Linear Systems by Graphing. Chapter 5 is all about systems of equations. And a system of equations is a vocabulary term. It's a set of two or more linear equations in the same variable. So what I'm talking about here is it could be something like x plus 3y equals 6 and 2x minus 7y is equal to 15. Now that's just a basic example. Basically what it means is you're going to have two equations or more, and you're going to have them on the same coordinate plane. So basically what the graph of this would look like is something like this. Now I have no idea, if in fact that's what the graph looks like. Probably not, but it could be something along those lines, okay? The solution to a system of equations, because really any system has a solution, or most systems have solutions. A solution is an ordered pair xy. Ordered pairs, remember, are in the form xy, and those have parentheses around them, that satisfy both equations. Okay, so what we're really looking for when we're talking solutions, when it says solve the system, when it says solve this, what we're really looking for is this point right here. Whoops, let me redraw that here. It's this point right here. It's that place where they intersect. Okay, because if a point is going to satisfy both equations, it means that point is on both lines, and the only point that is on both lines is that place where the two lines cross. Okay, so the first couple of examples here are going to be pretty basic. Tell whether the given ordered pair is a solution to the system of equations. So the ordered pair that they give you is 2, 5, and then the system they give you is x plus y equals 7, and 2x minus 3y is equal to negative 11. Now, if it's a solution, it's going to satisfy both equations. So what we need to do is we need to plug 2, 5 in for x and y into both equations. And what we really need to do is just do one at a time, because if it doesn't work for the first one, we don't need to go and check the second one, because it's got to work for both. If it doesn't work for the first, it doesn't matter if it works for the second or not. It's got to satisfy both. Okay, so we'll do the first one here in red. So the x value is 2 plus my y value of 5 equals 7. Now obviously this is a pretty basic one. 7 is equal to 7. That checks out. Okay, so once we get a true statement for the first one, then we need to go check the second one. Okay, so we'll plug 2, and then we got an x value of 2 minus 3 times my y value of 5, and we're going to see if that's negative 11. Whoops, negative 11. 2 times 2 is 4. Negative 3 times 5 is negative 15. Let me rewrite that. Negative 15. We're going to see if that's negative 11. 4 minus 15, when you do subtract that, it is negative 11. So negative 11 equals negative 11. That one also checks out. So the question, or the directions say, tell whether the given ordered pair is a solution. Yes, it is a solution to our system. It's where the ordered pair 2, 5 is where these two lines intersect. It's where they cross. Okay? Let's try another one here. Number 2, negative 2, 0. In our system, y equals negative 2x minus 4, and y equals x plus 4. So let's check the first equation. We'll do that one in red. So my y value is 0, is equal to negative 2 times my x value of negative 2, and then minus 4. Negative 2 times negative 2 is positive 4, and 4 minus 4, that one does check out. That is 0. We'll do the second one here in green. So we got my y value again of 0 equals my x value of negative 2 plus 4. Now negative 2 plus 4, that is positive 2. Now, clearly 0 is not equal to 2, so that is not going to work. So if the ordered pair they give you works for the first one but does not work for the second one, your answer is not a solution. Or you could say false or not true or something like that. It has to be true for both. Okay, if it works for the first, try the second. If it doesn't work for the first, you don't need to worry about the second one, because it's got to work for both. If it does not work for both, then it is not a solution of your system. Okay, so the title of the section was Solving Linear Systems by Graphing. Here's how we do it. Pretty basic. Step number 1, graph each line in the same coordinate plane. Okay, the coordinate plane is just the XY plane that we graph lines on. Step number 2, estimate the point of intersection. And then step number 3, verify the solution algebraically. I'm going to be very honest with you. Solving by graphing is the most labor-intensive method to solving systems of equations, especially by hand. It's very tedious. It's very time-consuming. I'm not a big fan of this. So I'm going to show you one by hand, and then I'm going to show you one using technology. Okay, so the first one I will show you by hand. Solve the system by graphing. We got y equals negative 2x plus 5 and y equals 4x minus 1. So if we're graphing, first thing we need to do is we need to build ourselves a coordinate plane. Okay, so I'm going to go, let's see, 1, 2, actually I'm going to redraw my X and Y axis here. I'm going to draw this just a little lower. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 1, 2, 3, 1, 2. Okay, so the first one I'll do in red. So I got negative 2x plus 5. So I'm going to go up to 5 on my y-axis and make a point, and then my slope is negative 2, which means down 2 and to the right 1. So down 2, right 1, and I got another point there. So let me erase all those extra, erase all these extra little marks. Okay, so down 2, right 1. I can keep going down 2, right 1 more. Down 2, right 1 more. Now I'm out of space on the right. Instead of going down and to the right, I could also go up and to the left. Okay, I can draw this line. That's okay. That's very poorly drawn, but it is a line, or supposed to be. With graph paper and a solid surface, it would be much easier. Okay, the second one, we'll do that in green. 4x minus 1. So we start here at negative 1 with our y-intercept. Our slope is 4, so that would be up 4 and to the right 1. So 1, 2, 3, 4, right 1. That's very, very convenient for us because we already have a point there. Okay? I don't think we need to go any farther because clearly we can see our potential point of intersection. Okay? That point of intersection looks like the point 1, 3. Okay? To be sure, though, we need to go in and check 1, 3 in our system of equations. So let's start with the top one, the red one. We're going to have 3 equals negative 2 times my x value, which is 1, plus 5. Negative 2 times 1 is negative 2, plus, not 1, plus 5. Negative 2 plus 5 is equal to 3. So that point checks out for the red one. Now, we need to go check the green one, and I'm running out of space here. So let's see, my y value is 3 again. My x, let's see, I got 4 times my x value, which is 1, and then minus 1. Let's see, 3 equals 4 times 1 is 4, minus 1. Yeah, that's going to check out. Okay, so this point right here, 1, 3, is going to be our solution for the system in example number 1. Now, example number 2, I'm going to show you a shortcut. 2x plus y equals 5, 3x minus 2y equals 4. If you wanted to do this by hand, you certainly could. Like I said, it might take you a while. It's a little more labor intensive. I'm going to show you a little shortcut. And that shortcut is what's called Desmos. Okay? If you search Desmos in Google and look for graphing calculator, it's the first thing that pops up. So what you're going to see is you're going to see a screen that looks like this. Okay? Let me slide this up a little bit. Over here on the left, you're going to type in your two equations, 2x plus y equals 5, 3x minus 2y equals 4, and it will show you different colors. The red line over here is the first equation, the blue line is the second one. If you had more, there would be more colors. But what we're really looking for is this point of intersection. So if you hover your mouse right over that point or click on it, it will tell you the coordinates of your intersection to 1. Now, could you verify that? Yes, but if you typed it in correctly, I'm pretty sure technology will give you the correct answer. Okay, so we can just say for example number 2, our solution is 2, 1. The final thing the final question or example in this section is a story problem, and the textbook wants me to do this through graphing, and this example I don't really find graphing very useful because there's actually too much information to need a graph. Okay, so let's get into this. For the first tour of the day at a museum, 4 child tickets were sold and 8 adult tickets were sold for $128 total. For the second tour, 6 adult tickets were sold for $72. Find the price of each type of ticket. Okay, so for tour number 1, okay, so for tour 1, we know we sold 4 kids tickets. We know we sold 8 adult tickets, and we know we made a grand total of $128. Okay, we're going to assume that X is equal to the kids ticket, or the price of the kids ticket. Y is equal to the price of the adult ticket. We're going to assume that they are not the same, so we have to use 2 different variables. Okay, so actually, you know what I'm going to do? I'm going to erase this, and I'm going to write some qualifiers here. So we're going to say that X is equal to the price of the kids ticket, and then Y is equal to the price of the adult ticket. okay? And then I'll write the first equation again. So tour number 1, that was $4 or 4 tickets at X dollars plus 8 tickets at Y dollars, and we made, let me make a better equal sign here. We made $128. For the second tour, it says we sold 6 adult tickets for $72. That means we didn't sell any student tickets or kids tickets. So what we can say is that we can say that 6y is equal to 72. Now, the reason I don't like graphing this is because we have basically a single step equation right here for tour number 2. Okay? So what I would do, what I see right away, is let's solve the second equation for y, because that's going to tell us the price of the adult ticket. Okay, so if we divide 72 by 6, what we're going to come up with is 12. So we know the price of an adult ticket is $12. Well, once we have this, what we can do is we can take this and plug it into our first equation, because we know that adult tickets are $12 a piece. We know we sold 8 adult tickets. Let's find out how much we made from the adults and then figure out kind of how much we made from the kids' tickets. Okay, so we're going to have 4x plus 8 times my y value. We know y is the price of an adult ticket, and that was $12, equals 128. Okay, 8 times 12, so 4x plus 8 times 12, 8 times 2 is 6, that was 16. 8 times 1 is 8, plus 1 gives me the 96, equals 128. Okay, we'll need to subtract 96 from both sides. 4x is equal to, that's 32. We'll divide both sides by 4, and we're going to come up with that the kids' tickets are $8 a piece. Okay, so we'll say x is equal to 8, y is equal to 12. Kids' tickets are $8 a piece. Okay, so if we wanted to write an ordered pair, it would be 8, 12. Now the graphing version of this, what it would look like is something along these lines. Okay, and this point right here is 8, 12. Okay, if you want to see the actual graph in action, just let me know. But I think with this specific example, graphing is a little excessive. It's not necessarily the most efficient way to solve this problem. This one, kind of lays it out there for you. It tells you the cost of the adult ticket pretty easily, and then you just need to use that information to find the kids' tickets. But like I said, section 1, the solving by graphing, is not my favorite subject or favorite way to solve a system of equations. It's not going to be heavily tested because it does take a while when you have to do it by hand. I'm going to focus more on sections 2 and 3, the algebraic versions or the algebraic methods to solving a system of equations.